Welcome. In this video, we'll be looking at the stability compensation. So we'll be looking at taking a circuit that's going to be put into feedback and adjusting the poles, the dominant pole, so that the overall system becomes stable. So let's get started. So as I mentioned, we're going to be looking at stability compensation. So how to stabilize a feedback circuit. So say we're given an open loop LOS, and how should our poles be added or moved in order to stabilize our closed loop system? Note that with our open loop system, it's really not feasible to remove the poles. Ideally, that would be the best way to stabilize the system, but it usually can't be done because these poles are due to parasitic capacitances, and they occur and they cannot be removed. They can be moved to lower frequencies, but it's very hard often to move them to higher frequencies without a lot of power or other techniques. So we can't remove these poles, but we would like to make the overall system stable. So let's look at an example here. So here's an example that we'll look at. In this example, it'll be a third order system where LOS, we're showing LOS here, and this is the magnitude of L of j omega in dB versus frequency. So its DC gain is given by L naught, which is, we'll assume is fairly large, and that we have a pole omega P1 occurring here, another pole omega P2 occurring here somewhere, and omega P3 occurring somewhere around here. But notice all these are above where the gain has reached 0 dB. So let's assume we've just built an amplifier like this, and all of these are above where 0 dB occurs. So what we see is that this will be minus 20 dB per decade here. This will now be minus 40 dB per decade because of the extra pole, and this will be at minus 60 dB per decade because of the other extra pole. And that if we looked for where omega 1 occurs way up here because that's where we finally reach 0 dB. We'll also make the assumption, for simplicity, that omega P1, omega P2, and omega P3, they're all widely spaced apart. So first let's look at this system, and let's imagine that we just put this into a feedback system. So this was our LOS and we connected it in feedback. First we note that it's going to be unstable because our phase margin will be less than 0. And why do we say that? Well, we note that omega P1 here will add minus 90 degrees of phase. Omega P2 will add another minus 90 degrees of phase because each pole adds minus 90 degrees of phase. So we're already at minus 180 degrees and we're not at omega 1 yet. Omega P3 here adds 45 degrees phase right at this location. So when I was saying it was at minus 90, so what I was mentioning is omega P1 adds 45 degrees phase here, but once we're a factor of 10 higher, it's approximately minus 90 degrees. Same with omega P2, it adds minus 45 degrees here, but once we're a factor of 10 higher, it's almost 90 degrees of phase. So somewhere around here, we're at minus 180 degrees of phase. But we know then at omega P3, we have another 45 degrees of phase right at omega P3. So we have another 45 degrees here at omega P3, and we still have not reached omega 1. So we're at minus 225 degrees of phase at omega P3, and we haven't reached omega 1 yet, so we definitely have a negative phase margin. And recall, we did say that these are widely spaced, and that's why I can say that by the time I reach omega P2, we're already at minus 90 degrees because it's at least 10 times larger than omega P1. So, as I mentioned, omega 1 is greater than omega P3, so our phase is going to be less than minus 225 degrees phase, and our phase margin therefore is going to be less than 0. It'll be that phase might add 180, which is certainly going to be less than 0. So now our goal is to modify our loop gain to achieve a 45 degrees phase margin. As I mentioned before in the previous video, normally we'd like our phase margins to be greater than 60 degrees, But just for simplicities, let's assume it's around 45 degrees that we're happy with here. So at least we can make it stable. So let's look at two approaches here. The first approach is method 1. So the first approach is we'll add an extra pole, omega p0. So the problem with this is omega 1 occurred too late. So if we can add a pole earlier over here, then omega 1 can occur earlier. If we make a pole even earlier than this, if we add a new pole over here, then omega 1 would now occur at this location. If instead we made omega p0 even earlier, say down here, then omega 1 is going to occur even earlier. And we can move omega 1 to the left as much as we want by moving omega p0 to the left. So we're going to add a new pole omega p0, and that's our new pole over here. And this is going to be our dominant pole because it's the lowest frequency one and it's at a much lower frequency than all our other poles. So it's our dominant pole, and that's omega p0, and we've added this into our circuit. Now we want to make the overall system stable, so let's add it such that as it goes down, omega 1 occurs at approximately omega p1. So this is dropping off at minus 20 dB per decade. And this will be dropping off at minus 40 dB per decade, and this will be dropping off at minus 60 dB per decade, and so on. So we'd like omega 1 to occur at around omega p1. Because if we do that, then our phase margin, what we'll see is we'll have a phase margin of approximately 45 degrees. Why do we get that? Because as we said before, is that we'll get minus 90 degrees due to omega p0, so that'll give us a 90 degrees phase. Omega p1 will give us another 45 degrees phase at this location. And if omega 1 also occurs at omega p1, then we'll have minus 135 degrees phase, and minus 135 degrees minus negative 180 is 45 degrees. So we end up with a 45 degrees phase margin in this case. So that satisfies our phase margin. And then if we look at our closed loop bandwidth, turns out our closed loop bandwidth is approximately equal to omega t, or the omega 1 of the loop gain. So if this occurs, if our 0 dB frequency here is also omega p is approximately equal to omega 1, then our closed loop bandwidth is also equal to omega p1, or omega 1. And we get that from recalling that omega p prime, the closed loop bandwidth, is 1 plus L naught times omega p0, which is this value over here. And if you recall, that's going to be approximately equal to omega p1 here. So that was one approach to do it. The second approach, which is the preferred approach, so this is a better approach, is to look at our circuit in more detail. So find the circuit node that is responsible for omega p1 and move omega p1 to omega p1 prime by adding some capacitance at that node. So don't just introduce a new pole, but try to move one of the existing poles and move the lowest frequency pole. Don't take one of the higher ones, take one of the lower frequency ones. So we'll be taking omega p1 prime will become our dominant pole, and then omega p2 becomes our non-dominant pole. So what we'll be doing is taking this pole here and moving it to the left, so that once we finish that, we'll have omega 1 will occur around omega p2. So graphically that will look something like this here. So we have omega p1 now, which has moved to the left. Omega p1 has moved to the left to become omega p1 prime. So this pole has been moved to there, so we don't have to worry about it as a pole anymore. And this now becomes our dominant pole, omega p1 prime. And then we make it so that the omega 1 now, our non-dominant pole, occurs around omega p2. So this becomes our non-dominant pole, omega p2. And again, our phase margin is again going to be 45 degrees because we'll get 90 degrees due to omega p1 and a 45 degrees due to omega p2. And so we'll end up being 45 degrees away from minus 180 because we'll be at minus 135 degrees. Now the benefit of this approach is our closed loop bandwidth now, instead of being omega p1, is now omega p2. So it's increased. So we've made a faster circuit by just being a little smart about how we add our how we move a pole rather than adding an extra pole. Now one thing we should point out here is that everything we've done is fairly approximate, mainly because omega 1 really only roughly occurs in omega p2. We know that if the if omega p1 prime is much smaller than omega p2, then certainly our phase will be minus 90 somewhere 10 times higher than omega p1 prime. It's going to be approximately minus 90, and the higher we go, the closer it's going to be to minus 90. So right at omega p2, we'll certainly have a phase of an extra 45 degrees. So we'll be in new minus 135 degrees by the time we reach omega p2. But omega 1 will actually occur a little bit left of omega p2 because that comes in, it's not a straight line the way it's shown, it's actually curved, something like that. So there'll be some, omega 1 was really only approximation here. And we'd like to get a better estimate, because if we'd like to change our phase margin not to be 45 but to be some other value, we'd like to get a better estimate that relates our phase margin, omega p1, omega p2, and our loop gain value, the DC value of the loop gain. So first we'll look at just a relationship that relates the phase margin, omega 1, and omega p2, the non-dominant pole. So consider a loop gain, which is L naught divided by 3 poles here. So the denominator has 3 poles, omega p1, omega p2, and omega p3. We're going to assume that L naught, the DC gain, is much greater than 1. So it's 100, 1,000, 10,000, something like that. We'll also assume that omega p1 is much less than omega p2, which is much less than omega p3. So they're fairly widely spaced apart. And we recall that by definition, omega 1 is the frequency where the magnitude of the loop gain is equal to 1, by definition. Now, since the loop gain is much greater than 1, we have that omega 1, this frequency here, is going to be much greater than omega p1. We'll also assume that we want a phase margin which is going to be greater than 45 degrees, which means that omega 1 is going to be less than or equal to omega 2, so it'll be some value a little bit less than omega p2, but it's going to be much less than omega p3, because omega p3 is much greater than omega p2. But omega 1 will be some value, it won't be greater than omega p2, and it'll be some value which is less than or equal to omega p2. And that's because of our phase margin is going to be greater than 45 degrees here. So we really need to take this equation here, the top, and modify it for the region when omega is much less than omega p3 and much greater than omega p1. So we modify it for this region here, for when omega, frequencies of interest that we care about, because that's where our phase omega 1 is going to occur and where our phase margin will occur. And it's going to be much greater than omega p1 and much less than omega p3. So if we look at this equation here, if omega is much greater than omega p1, we can ignore this one term here. And if omega is much less than omega p3, we can ignore this term here. So then we can replace this loop gain with an approximate formula, which is shown here, where we just have s over omega p1, 1 plus s over omega p2, and we can ignore the omega p3 part of it. Now, we're interested in the phase margin. So we'd like to find the phase at omega 1, where the loop gain goes to 1. So let's just look at that for a second. So we know that's going to occur at 0, which is the phase of the numerator, minus the phase of this value. The phase of this one is going to be minus 90. So this will be 90 because it's j omega over omega p1. So it's just a complex value only. And minus the phase, minus the phase of this value. The phase of the last one is going to be arctan of omega 1 over omega p2 because s has been replaced by j omega. So we have that the phase at j omega 1 is given by this equation here. That means that we have that our phase margin, by definition, is this phase minus 180. So that phase plus 180 degrees. So if I substitute in this into here, we end up with this equation shown here. So finally we can write that the phase margin is given by 90 minus the arctan of omega 1 over omega p2. And this relates omega 1, omega p2, and the phase margin. So it's just the ratio of how far is our non-dominant pole, which is omega p2, higher than the unity gain frequency for our loop gain, omega 1. Now, it's useful to define a term k sub pn. So this is a constant, a value which is just the ratio of omega 1 relative to omega p2. So then we can rewrite the above equation by it's the phase margin of 90 degrees minus the arctan of k sub pm, where pm stands for phase margin here. The reason we want to define this is we'll see that this is a useful term to use in our next part, where we want to do a relationship that it now includes omega p1. So next thing we want to look at is relating omega k sub phase margin, or k sub pm, omega p2, L naught, and omega p1. And recall that this will be the ratio, will depend upon the ratio of omega 1 and omega p2 and the phase margin that we need. Actually, it's the ratio of omega 1 and omega p2, which will dictate the phase margin, I should say. It will dictate the, it's a direct relationship between k sub pm and the phase margin. So if we know k sub pm, we know the phase margin. If we know the phase margin, we know k sub pm. But we wanted to bring in omega p1 into this now relationship. So again, we use our approximate equation for L of S, which is given by here, because again, we're looking at frequencies that are much higher than omega p1. And we have that's where the gain of the loop gain becomes equal to 1 at j omega 1. So if we look at the magnitude of this for S equal to j omega, we have it's the magnitude of L naught, which is just L naught, divided by j omega over omega p1, which will be just omega 1 over omega p1, and divided by the magnitude of this when S equals j omega, which will be given by this equation here, 1 plus omega 1 over omega p2 squared to the 1/2. So this becomes the magnitude of that for S equals j omega. And we're letting S remember we're letting S equal to j omega 1. So we now have this formula, but recall that omega 1 here is given by this equation, which omega 1 is equal to k sub pm times omega p2. So we can replace this omega 1 by k sub pm times omega p2. This is still omega p1. You have 1 plus k sub pm squared to the 1/2. If we then just solve for omega p1, because we'd like to know what frequency we need to put our dominant pole to, given a phase margin and a non-dominant pole frequency. So given an omega p2, our non-dominant pole frequency, given a phase margin, which will determine k sub pm in this part, and given the DC gain of our loop, we can now determine what the low frequency dominant pole should be. So here's an example. Given that our non-dominant pole is equal to 100 megaradians per sample, 100 megaradians per second. Our DC gain of our loop is 1000. We want to find the dominant pole frequency so that we end up with a phase margin equal to 60 degrees. Using the equation we have above, the phase margin is 90 degrees minus the arctan of omega 1 over omega p2, we have that our phase margin is given to be 60 degrees, so phase margin is 60 degrees, which means that just taking this equation here and taking the arctan to the left and the 60 to the right, we have that the arctan of omega 1 over omega p2 should equal 30 degrees. Now we can take the tan of both sides. If we take the tan of both sides, we end up with omega 1 over omega p2 is the tan of 30 degrees. And that turns out to be the square root of 1/3. So in this case, we have that omega 1 should be the square root of 1/3 times omega p2. Or in other words, k sub pm is equal to the square root of 1/3. So that's due to the 60 degrees phase margin that we want. We now know what the relationship is between omega 1 and omega p2, our non-dominant pole. We can next use our next equation, which was shown here, and put that one in. So just repeat it in this location here. And we have the k sub pm is the square root of 1/3. Omega p2 is 100 times 10 to the 6th. 1 plus k sub pm squared is 4/3. Take that all to the 1/2. And then divide that by L naught, which is 1000. And it all works out to be 66.7 kiloradians per second. And that's where our low frequency dominant pole should be placed in order to get a 60 degree phase margin, assuming our non-dominant pole is at 100 megaradians per second. Now, it turns out that another thing we should know about compensating circuits is we can make use of Miller compensation and something called pole splitting. So it turns out this is a technique that actually extends our bandwidth a bit, but more importantly, it helps to reduce the size of the capacitances that we need to add in order to stabilize our feedback circuit. So consider this circuit here. So it's a common source amplifier being driven by a current source I sub in, which might be another transistor, has a resistance R1 over here, and a load resistance RD, actually a load resistance RL, and a drain resistance RD. We can model this as this circuit shown here. We still have our input current, R sub 1, and we'll assume that there's two capacitances associated with this. There's a capacitance here, which is C1, which is a parasitic capacitance, and a capacitance over here, which we'll call C2, which is also a parasitic capacitance. So these are capacitances that are always there, going to ground. And we'll ignore the gate to drain capacitance for a second. So if we include those two capacitances, so we have C1 and C2, and we'll also define R2 to be equal to the load resistance in parallel with RD in parallel with the R naught of our transistor. And as I mentioned, C1 and C2 are parasitic capacitances. So this becomes our model for this circuit, and this has two poles. It has a pole due to C1 in parallel with R1, and that pole is going to be at a frequency of 1 over R1 times C1, but also has a pole over here, which is C2 and R2, and that pole frequency is going to be at 1 over R2 times C2. So we have two poles in this circuit. If we wanted to compensate this, we'd have to decide which one was the lower frequency of the two, and then we would add more capacitance onto that one in order to compensate it so the overall system would be stable. Now let's look at the same situation, and we'll add this extra capacitance here, C sub F. C sub F is a compensation capacitance or feedback capacitance. So now, it turns out that this is really just adding a capacitance right here, C sub F. And if we analyze this circuit and look for the new omega P1 and omega P2, and you go through some nodal analysis, you'll find that omega P1 prime, the new omega P1, is 1 over GM R2 times CF times R1. This is assuming that GM R2 CF is much larger than C1. So the actual circuit, the actual equation would actually add in a plus C1 R1 here, but this C1 is generally much smaller than this whole term over here. So we can typically just ignore that part of the circuit, of the equation. And we can see that that's the case because we have a Miller capacitance here. The gain from here to here is GM times R2, which is the impedance seen at the drain of the transistor. And so that becomes the GM R2 times CF, because it increases the capacitance by approximately that size, that gain factor. If you also do some analysis, you'll find the other pole, omega P2 prime, is approximately given by this equation here. So what you see here, though, is that as you increase C sub F, so as the capacitance here becomes increased, then this value here, this omega P1, is going to get lower. So it decreases. However, you look at this one, because we have CF on the top and CF on the bottom, but this one tends to dominate because it's just a multiplicative, and this has an extra term to it. This actually, this one actually goes higher as we increase CF. So this one becomes lower, and this one becomes higher. So we're actually splitting the poles. So what we see is that, as I mentioned, omega P1 prime decreases, but omega P2 prime increases. So our poles are splitting further apart. So that's actually better than just adding a cap in parallel with C1, because we'll get a higher bandwidth with this. Our non-dominant pole is increasing to a higher frequency, which is helping us to get more bandwidth in our final circuit. The other added benefit is we need a much smaller capacitor size, because we're using our Miller effect and helping our CF to appear much larger. We're getting this extra factor of GM times R2 multiplied by CF. So we get that Miller gain effector, and we don't need nearly as large a capacitor than if we had just simply added, instead of doing this here, if we just added a capacitor here, we would have needed a much larger capacitor, because it would have to be at least GM R2 larger in order to get the same effect. So this is commonly used in many of the op-amp circuits and feedback circuits in general. Final thing I want to cover is just estimating the settling time in a feedback system that has a phase margin greater than 60 degrees. So I mentioned the phase margin here greater than 60 degrees because if that's the case, then we can see that the settling behavior will be more like a first order system. It won't have a lot of ringing associated with it, and so we can approximate that roughly as a first order system. So since our phase margin is greater than 60 degrees, and the higher it is, closer to 90, the more it'll look like a first order system, we can approximate L as just being a first order system, where L of S is our loop gain. So we have a L naught, a low frequency pole, and it'll just drop off at minus 20 per decade along this slope here. Oops, sorry about that. And we know from before that for the loop gain much greater than 1, the unit gain frequency here, omega t, will be approximately equal to just L naught times omega L. We've seen that a number of times before. But we know there are 1 plus the loop gain equal to 0. If we find the roots of this, that'll be the pole of the closed loop system. So if we set 1 plus L of S, where this is L of S here, equal to 0, we find that the pole is now located, closed loop pole, so the closed loop pole is located at minus 1 plus L naught times omega L. But we did say that L naught is much greater than 1. So we can ignore the 1 here. So the pole is approximately, again, since L naught is much greater than 1, that closed loop pole is approximately just minus L naught times omega L. But we said above that omega t was approximately L naught times omega L. So what we have then is that since omega t is L naught times omega L and that closed loop pole is also at minus L naught times omega L, that our closed loop pole is just approximately minus omega t. So when we have a phase margin that is greater than 60 degrees, we can say that the unity gain frequency of our loop gain will be approximately equal to our bandwidth of our closed loop system. And since our closed loop system pole frequency is equal to omega t, the time constant, if we look at the settling behavior, will just be 1 over omega t. So if we wanted to figure out what the step response would be, the time constant tau would just be 1 over omega t. Okay, and that ends this, this video, and thank you for watching.